So now we will talk about the extension I was talking about. So this is at one location. I know how to calculate pulse repetition rate. I know what is the depth of imaging that I want, but that is at one location. A direct extension of that is what is called as M mode or motion mode. What is motion mode? Oh, now don't get confused. This motion is not moving the transducer. The beauty about this mode is, I told you that you get only at one location you are sitting, you are getting in the z direction, in the depth direction, the echoes, right? That is what your A line. So what happens if that echo, that interface is moving? So I sit in the same location, but there is a motion of the interface, right? So where do you think this situation is available in your body? Well, if I sit in one location, of course we talked about Doppler blood velocity, but there it was mostly scattering motion that we talked about, not really the interface as we covered right now, right? Where else? Oh, your heart, right? If I want to heart, you have flaps that are opening and closing, the heart tissue itself, right? If I am hitting it, sending my pulse and sitting in the same location, and this heart is pumping, right? That means the interface is close, further away, close, further away. So I am sitting in one and listening to the echo. It will seem like the wall is going to come towards you, move toward away from you, right? So if I do time trace, right, calculate the pulse. So we can calculate the pulse repetition rate. So of a 5 megahertz, right, loss is given. So I pretend I want to do this heart imaging. So I am given a transducer. How fast can I do? Just to get an appreciation for the number, if you have 5 megahertz, A is 1 dB per centimeter per megahertz. That means I am going to have my alpha to be 5 times 5 dB per centimeter, 5 dB per centimeter, right? 1 dB per centimeter per megahertz into 5 megahertz will give me 5 dB per centimeter. Loss appreciable here is 80 dB. So I can get L is 80 dB divided by 5, right? 80 by 5. Okay, so I can easily calculate my depth of penetration. Once you get the depth of penetration, you can calculate the 2D by 2 depth of penetration by C, right? If you apply, you can get your pulse interval or pulse repetition is going to be 3.75K or 3750 pulse per second, right? This is what I can do. So that means I send my first pulse, receive the echo signal, send the next pulse at after 0.267 millisecond, receive the echo, and I plot the time trace for it, right? My envelope signal, my A mode signal. How will it look if I do it such that along the path there is a heart or something that is moving, right? So you will get an image. This is one A line, right? So what is the difference? The amplitude mode, I showed you the envelope, right? Here, because we make it as an image, you encode the peak to be white and the valley to be black and everything in between to be your black and white, similar to the example problems that we did in when we talked about the introduction imaging, plotting a signal, 2D signal and image of a 2D signal, visualizing it as an image. You quantize the third dimension as a color. So here that is what is happening. So your amplitude mode, but this is one amplitude line. So this is 0, this is your skin and this is going into the tissue, into the body, right? So this one line is supposed to be one at one response to one pulse. I am sending the next pulse and placing it next to each other. So this is a time axis, this is your depth axis. So when I plot A line as a function of time, I get a motion mode. Why is this a motion mode? Notice that this interface is coming close going up. So, this is opening closing here, see. So, skin you do not have much oscillations. So, skin is not moving up and down that much. So, therefore, it is not oscillating, whereas along its path there are several interfaces very weak, these are very weak scattering, right, whereas this prominent interface that is moving, right, within that path is, you can notice. So, you see how powerful this is. This can visualize if the flap is opening, moving, right, the frequency with which this. So, this is your ECG, right. So, you can essentially look at this and say, look, you can actually get very powerful information even though it is just amplitude at one location you are keeping, you are just plotting it as a function of time, your A line as a function of time, different pulse, right, you are just stacking next to each other. This itself tells you the whole range of motion of the tissue that is opening and closing. You can get that information. You can get the frequency of opening and closing. All these are vital parameters, right. So, you can get all that. So, you can visualize that information from this image. So, this is a motion mode. Mostly you see this in the scanner as one of the options, and it will be typically used when you are doing echocardiography. That is a whole field. Cardiography is relating to your heart. Echocardiography will be a different department in a hospital. Specialized scanner will be there. So, it is an ultrasound scanner, but echocardiography means it is same echo principle. It works as echo principle for the heart. Okay. So, in that you typically encounter M mode. Most powerful use will be what we call as brightness mode, right, or B mode. This is the sonogram, this is the typical image, the baby sucking the finger, right, the typical image that you see for ultrasound. That is a brightness mode. Like I said already, in M mode I just pointed out. What is that brightness mode? In principle, you have this amplitude mode, you have this envelope, right. If I stack that at different, I do that at different locations and quantize the amplitude into different brightness, white being the highest, the peak value, black being the floor value, anything in between is your gray value. So, it is encoded to brightness. So, that is why it is called as brightness mode. So, you start out with the same amplitude mode signal, right, which is very straightforward from our imaging equation. Only thing now what we need to do is, so you got one A mode signal. Now, if I want to do image, what should I do? I should move the transducer, right. I move the transducer to the next location. So, for example, if this we talked about Z direction, depth direction. So, let us call this as your lateral or your X direction. So, I have to now step to some x1, y0, z0 and do the same weight. After your depth of penetration, you trace all that, you send the next pulse, go to the next location. So, I go left to right, I build my scan one line at a time, right. I build my scan one line at a time. So, transducer, I move the transducer. So, this is the pulse, right. So, for simplicity, this is what we put, but notice the challenge. So, if I want to do the scanning, this is how they used to do at the beginning, right. You have a transducer, how do I move this correctly so that it is registered, so I can get an image, right. So, your image, as you see, can be like this, right. Some organ is here, right, baby is here, for example, right. This is the image that you are building. So, you notice I can do this in principle. From what we have covered so far, you do this. In fact, this is how they did it. In fact, to do this more carefully, they had an articulated arm so that this goes in line. So, like how you have your engineering drawing, right, when you are exposed to an engineering first year course, engineering drawing, you have this drafts, right. So, likewise you have a transducer that will be attached to a arm, and the doctor has to basically move it, but it is kind of engineered such that it will move in straight line, right, at certain velocity. So this is how they used to do it. Okay, so that way it is registered, you can move, but you notice the challenge. So this is straightforward, we are not going to spend more time on this. This is how it started. So you can imagine the same A mode, what we saw in the previous slide is M mode. Similar thing, if I do the same amplitude, quantize it, put brightness, this will be at one location, next location I move, I do this. So this will be your x direction, this will be your z direction, I get an image where all the scattering will be different, right, because the interface is like this. So they will be scattered, but then the interface reflection coefficient will be probably more close here, more farther away here, farthest away here, right. So that is how you see the outline of the baby. So wherever there is an interface change or some other organ, right, this is how imaging is done. The challenge here which we will try to address and overcome is, if you do this, you notice how do I step. One parameter we talked about, how soon I send the next pulse, right, pulse repetition rate. But now the point is, how much can I step, say if I am going from left to right. Ideally I need to be as close as possible. So idea is I am building this image line by line. So first I get one time trace here, next this transducer is moved like this, right, I get the next, even though the transducer is moved, right. So let me not clutter it here. So you do the same process, say I am here. So I can have different lines stacked next to each other, so I can form an image. But this is very simplistic, right. You see the challenge. When you have a transducer like this, what is going to happen? Beam pattern, it is going to diverge, right. It will start and then it will, we talked about this, diverge, right. Not only that, then you will say, oh, we talked about having a lens. So we talked about having a lens. The lens will do okay, depending on, you are still talking about like this. Then you might say, oh, if this is the case, then maybe I can have a bigger transducer element. This will probably allow me to have more narrow, alright. But then if I have this much, if I step in the lateral direction, how I have to still step as fine as possible, but anything finer than this is not going to be, right. This is the narrowest, right. So the narrower I step, that means I will have to do lot more lines to cover the same distance, right. So that means each location I am sending one pulse. If I have to construct a frame, an image frame which has how many lines, say for example typically we get say approximately 100 lines if you want to cover, right. I have to send 100 pulses, okay. But each pulse, how much I am going to cover? Oh, each pulse I am going to have certain width that it is covering. So if I want to have a good resolution in the lateral direction, I have to have as narrow a beam as possible and I have to step as fine as possible, right. So all that is going to take more number of pulses, and if you are to do your beam width shaping, you can only do the shaping so long, right. If you get this narrow, it is going to be wider only at this location, probably you will have reasonable narrow width. Anything beyond that, it is going to diverge again, right. This is the complexity. So this is how you get it. So one of the other important parameters just to put all, and of course that means you have to start your motion, stop your motion get the data till depth of penetration at that location, I have to go deep and come back. So that means I have to maybe halt here, maybe I can move slow, but the point is there is a time to have this motion taking place, start, stop, or go slowly so that you can receive from the deepest location. Whichever way you look at it, if you, one another constraint is your, apart from your resolutions that are dictated by the frame beam pattern, right, to execute the scanning also takes time. So one of the important parameters is, when you talk about one dimension, we talked about pulse repetition rate. Now if you are talking about image, you always encounter this frames per second, right, frame rate. That's what you will encounter. What is the frame rate? How much time does it take to get one frame, image frame? Here in one image frame you get by sending multiple pulses, one pulse at one location. So the number of lines I have, that many number of pulse I need to send. Okay. So what is your frame rate? What is your frame rate? Number of times your pulse repetition rate, and how many pulse do you need to send to obtain one frame? That's your frame rate. Okay. Of course, this is linear motion. You could also do, right, sector, right? You connect this and you can articulate it at an angle. So that way, if you do it this way, your image will be like in this format, right? This will be rectangular image. This will be a pie kind of image, sector image they call. Okay. So this is how it was done. I mean, the reason I just want to leave it at here is, this has a lot of challenges, as you can see. I can have only one focal location because the lens is going to be manufactured with one particular curvature. So I am going to have only one focal depth that I can have. So all my, and then I cannot, if I have a big one, I can have narrow, right? But then I am still averaging over all the area to get one thing, right? And the more wide and more narrow I have, more shorter will be my depth of focus, right? So my resolution will be spoiled. But if I have the other hand, if I have a smaller transducer, then the divergence will be an issue and I cannot have focusing effect, right? So, and of course that is the case, my step size also should decrease, and therefore your time for acquiring the data is going to increase. So all these trade-offs makes it that it was the way it was done until 90s, for example, right? So you had your frame rate also coming into picture. You wanted to see real time, you want to see the baby sucking, right? So that means you have to do it faster than you have, do better quality than, so the whole benchmarking of ultrasound images changed, right? Instead of scanning it mechanically, the whole idea of electronic scanning using array transducer, having multiple elements, instead of having only one transducer like this and moving, concept of array transducer kicked in the 90s, and that kind of changed the whole landscape of ultrasound imaging. So what we will do here is just take a pause and then continue with array transducer and wrap up the image formation and image quality. We are interlacing already, right? So in that sense, image quality and image formation in relation to how we are acquiring the data, right? How we are scanning, we have coupled it. Okay. So we'll stop here. We'll wrap up the ultrasound, introduction to ultrasound imaging in the next 45 minutes. So let us continue with the beam mode operation of an ultrasound. This is predominantly the most dominant imaging mode. When they say ultrasound image, this is the mode that typically comes to mind. So amplitude mode has its role, but when we talk about images, we typically associate an ultrasound image with what is a B mode image, which is brightness mode. So what we did see is carrying along with the same logic of having a mode, but then translating the A mode, right, scanning the A mode, we could create a image. However, right, so this is what we saw. So you could use this transducer, you could get one A mode, right, the A line we call amplitude mode, you operate amplitude mode, and the next pulse you move this, and this way you could scan and get a whole X by Z image, right, Z being the depth, X in this direction is the lateral direction we refer to. So this will be the image. However, this has lot of, I mean, this is how it was practiced, right. Of course, with instead of just moving it with hand, they used to have an articulated arm so that you go in a line. But then there are a lot of disadvantages, right. So this is not currently in vogue. However, the logic is very powerful because we covered physics and then we translated this to this use of it. So what are the things that we were able to do here, which we see the reason for doing it, but is kind of a disadvantage or is kind of a limitation that would allow us to seek for better advancements in instrumentation. Okay. So first is, can we avoid the mechanical scanning? Yes, the idea is the transducer is helpful. It sends the wave, receives the wave, we can get the A mode, we gone through the physics, right, it made sense. But then to engineer it to an application, the instrumentation, there was a limitation. So can we avoid, instead of doing this mechanical scanning, very similar if you look at it from first generation CT to the advanced CT that we covered. Similarly, so you had one transducer and the transducer had to be moved. Can we avoid this? In fact, there is a lot of disadvantages, right, because you have wear and tear of the mechanical parts, motors, and then you could have jitter error because you are moving, stopping, taking the data. So unless you completely come to a halt, you will still have start and stop, so there will be some errors. If you want to do that, how many times should you do that, right? So it will take forever. So the frame rate will be extremely slow. Okay, unlike CT or in electromagnetics, right, the wave here their speed was not an issue, whereas here speed is, the sound has to travel. So that is a very fraction, right, of compared to your light or electromagnetic waves. So frame rate will be severely limited if you have to stop at every location, wait for the deepest location to depth of penetration that we covered, right. So all that is a challenge. So ideally we want to avoid this mechanical scanning, that way maybe we could do better, right, on all these problems. We should be able to eliminate all these problems to the best possible extent. Okay, so that is to do with just mechanical design aspect or articulation. Is there anything to do with the image quality that we are limited by operating it this way? Well, we talked about focusing. What is the problem? Focusing was good. We could get our lateral width as small as possible, right, at the focus. But then the challenge was, you can have only one lens because there is a physical acoustic lens if you put it in front of the transducer. So each transducer will have one focus. So if you want to have a focus in different depth, for example, you need to take another transducer or just live with this. Move the patient, right, the object can be moved up and down so that it fits the focus. So in some sense it's very limited. You have only fixed focus, not just fixed focus on transmit, the waves that are sent out, even the receive, right, the echoes that are coming back, they are also going to have, you are going to have the fixed focus effect which was done for that particular curvature of the lens. So this is a big challenge. You want ideally all the images, all the pixels in this image to be at the focus, right. But here you are clearly limited. You have only one transducer which comes with a fixed lens, and therefore there is only one focus. So, so that is a challenge, right. Both transmit and receive use the same lens. So you have a problem. What else? Is there anything else that comes to your mind? From an image quality perspective, focus is a big issue, right. Well, Of course, other aspect was your side lobe reduction, right? We talked about having apodization. So, you could in front of the transducer, why give weight, same weight to the center and the edges? You want to give more weightage to the center, and as you go away from the center of the transducer towards the edge of the face, you want to have a smooth, right, Gaussian, right, we talked about that. So, you could have a material that does the apodization, but clearly you know from your signal processing, similar concept you would have been familiar with filter design, right, main lobe to side lobe or ripple effect. You have a rectangle window or a Gaussian window, right. Same logic I said is in the spatial aspect here. So, that means you know there are so many different windows that are possible, Hamming, Hanning, whereas if you end up doing one material which give preference weight to the center as opposed to the, you can have only one profile, you can have only one window function, right. So, that again fixed apodization. So, that is a challenge. I mean, we would like to increase the image quality, do the best possible. So, these are all major limitation, and so all of this got kind of this background pressure of doing better quality image in real time, overcoming these limitation kind of got addressed, and lot of migration, transition, lot of development in ultrasound as we see today took place because of advent of the array transducers. What do we mean by array transducers? Instead of one element that you have here, you have multiple elements, right. So, that is your, you can see I found this image in one of the journals where they talked about, it is a clinical journal where they talk about how to choose a transducer for a particular clinical application. As you can see, depending on the application, your size and shape of your transducer changes. So, you would see some of them, for example, here you will still use the single element that we covered so far, mechanical scanning. Why? Because say for example transesophageal, right, you have to send the transducer through the opening. So, in intravascular, right, you want to send it through the vascular blood vessel, so that you can go inside and see. So, all those things you cannot have, you have to have a size of the transducer that is small enough that it can go into the body. So, you could have, you have several different size and shape depending on the application, single element with mechanical articulation, right, two different types of probes that you see here. Okay. Predominantly what we will cover in this course is the underlying concept of how array is used to form an image. So, we will not go into detailed specific application transducers. So, we will cover generic, say for example, you have your linear array, right, where elements are positioned next to each other along a line. So, these are different elements, different piezoelectric crystals, independent crystals that are placed next to each other in this linear array form. This is called as a phased array. Here also you notice that it is the arrays, I mean the elements, individual elements are placed next to each other. It is also in line, but it is called phased array just to differentiate from linear array operation, because we will cover this phased array subsequently, because here you notice the size of the element will be different, and the distance between the elements is designed for a certain phase. Okay, so we will talk about that. That is why it is phased array, even though it looks linear. This is phased array because the elements are placed so that, you know, at a particular separation between them. The elements are separated by a particular distance in order to capitalize on the phase, to get some conditions on the phase of the waves that are coming from each element. So, we will talk about that. So, these are very popular. Of course, there is also a curvilinear, right, for abdomen, when you have larger area to cover, right, you want even bigger head, wherever you can place the probe on body, where there is no constraint on access. Okay. So, depending on the application, you have different probes. So, what we will cover is, our idea is fundamentals, just to get an idea on the subject. So, we have covered A mode. Instead of mechanically translating it, mechanically steering it, how do we do the same thing? How do we accomplish the same thing using this transducer array? That is what we will cover. So, next 45 minutes or so is probably where we will complete the module on ultrasound, is probably going to be the single most important piece of topic that you need to know in ultrasound, as far as ultrasound imaging is concerned, because this is where the jobs are. What we covered in the physics, what we covered with mechanical, the beam focus, all the concepts of physics and the single element transducer is necessary. But then most of the application, as you would see here, but for some specialized application, most of them have moved to array and digital, right. So, how do we, the physics that we have understood so far, the wave equation and what we said, how do we execute it? How do you engineer it using this transducer? How do you dictate this transducer to do the same physics that we covered so far, right, of focusing, scanning in different directions? How do you do that? That we will cover, at least give a tip of the iceberg kind of overview, okay, in this next 45 minutes. So, I think it is very powerful. Please pay attention. Then you look at several different animations, textbooks. I hope you cannot use this 40 minutes as an excuse and say, I listened to this module, so I have I expect it to be crystal clear in my mind. That is not going to happen. This, along with you going reading the text, different text, see animations in the website, you just go, these are very powerful material, several good animations are there. But once you have a formal orientation, you will be able to look at it with a critical eye and understand further. Okay. So, let us jump in first to see how we use this phase array. So, before we jump, we will have an overview. So, why do people use different transducers for different applications? So, your image format will also be different. So, linear array, you will get a typical rectangle, right. So, like this, whereas in phased array, you notice it is a pie shaped or sector shaped you get. How do we get this from your A line, right? So, A mode we will cover now. So, in fact, this we will not cover detail. This is something that we will cover in detail, and then this becomes one particular condition of the operation of this. Okay. So, we will start with phased array. How do we see from what you know so far, right? Do not worry about this lines, elements. If you had a single crystal of this width, right, what would you have? What have we covered? Oh, you excite, it will go, you get one A line. What you see here is, you have one A line, you have another A line, you have another A line, each one has been fired at a different angle. So, instead of this mechanical articulation like a sector that we talked about, here the same array is standing there, it is able to send to different directions and collect A line. So, let us see how it is done. Okay. So, why we are able to do? So, different functionalities, why we are able to do? The reason is here. Essentially what happens is, it becomes complex because now instead of having only one lead, right, we had a transducer, we had one wire coming out. So, you supply electrical voltage, electrical pulse, it will vibrate, sound goes out. When the sound comes and hits, it vibrates, you get your electrical out. So, there was only one lead wire. If you look at the previous piezoelectric crystal single element that we covered, piezoelectric transducer. Whereas here what you have is multiple crystals, each one has its own control, each one acts as an independent channel. So you have electrodes for each of the crystal. So now you see the challenge. If you have a smaller crystal, you have to have all the electrodes that are also correspondingly small. Not only that, there shouldn't be crosstalks, right? So you have many of these, then you have complexity goes up. But the point is, the advantage is you have all these crystals next to each other, each one can be excited. You can independently send electrical voltage here, and whatever hits this crystal alone, you will be able to receive the corresponding voltage and play with it, right? Corresponding signal you can get. So now you notice the advantage. Now I can independently operate all of this. So I can send, remember now your wave physics that we covered. So when you hit an element, right, you excite, what is happening? If it is a point source, you are going to get a spherical wave, right. So what do you see here? Now my elements are getting smaller and smaller, and many of them are placed next to each other. Instead of having one full transducer surface where we integrated, right, integrated over the full surface area S of x comma y, right, S of x naught comma y naught, right. So here you have many of them. So I could actually integrate only over the small area and it comes up. So in some sense there is a localization. So if only this is excited, this sends out a pulse wave, this sends another pulse, this sends another. So I have control over how to excite them, right, because I am the one who is supplying the voltage. So I can supply after a delay. So I could send them such that the plane wave front that we talked about, right, all of them start to go in a particular direction, right. So this is what we call a steer. So the advantage is you could do that. Not just that, why do linear fashion? I could give such that, right, I could delay, excite the elements with certain pattern such that you have focusing, okay. Concept is very simple. If I excite, we will cover this mathematically, but the idea here is, it's all very simple. You create a wave. So if you excite this, this is going to give a mechanical pressure wave. This pressure wave is going to start to go out, right. The moment it leaves, it is going to go out in the medium. So the idea now is, if I want to focus at a particular location, medium, let us assume, has some velocity c, right. So I know the time in which this is released. So time arrival of this to that particular location is going to be, ideally we want this wave and this wave and this wave and this wave, all of them should come in phase coherently at a particular location, which is your focus. So clearly you can see, I can manipulate, oh, this one I should send first because it has to travel a lot of distance, right, to come here, at least lot more than, this is the shortest path. So if I want everything to come to focus at a particular location, I can excite this such that this will be excited last because it has to travel the least distance, because all of them assume same speed in the material. So this I have to send earlier, this I have to send earlier, probably symmetric. Then what will happen? And then gradually reduce the time, right, send after some delay, you send this, and finally you send this guy. What will happen? All of them will leave the transducer at different times, but then they all will reach at a particular location at the same time, which is basically they are all focused, they all coherently add up at a particular location. So you can control all this. So advantage, now I don't need a physical lens. All I need to do is I should manipulate the time delay when I excite which crystal. If I play with that, I could get focus wherever I want, how much ever focus, how tight you want to focus, right. Everything can be manipulated by manipulating the sequence of excitation. Last part we talked about apodization. What is apodization? Weighting the amplitude, right. So that is no big deal. We already talked about when you hit the voltage part, maybe there only I can give more weightage to the center. As you go to the sides, I could reduce it. So I could have apodization function. With based on that, I could give the amplitudes at the transmit itself, right. So here I have a higher amplitude, as you go to the sides I have lower contribution. So in some sense the transmit apodization you can excite the way you want, you can try hamming, hanning, you can do whatever you want. There is no fixed apodization material, because I have control over all of the crystals separately, independently. I can give whatever same waveform at a different voltage, and the profile of this can be your window function, clear. So, it is all electronically done, okay, and that is that. So, all the major limitation that we talked about with respect to mechanical scanning, with the array, the advantage of having control of each of the crystals separately gives us the flexibility to overcome scanning, whichever direction I want I can scan, however I want to focus I can focus, whichever apodization I want to apply I can apply. Pretty neat, right? So let's see, let's jump in, let's see how to execute this. In principle you see this, but how do you calculate this? How do you what is the exact analytical formulation, right, to execute this. After this you can try out different things, but the general idea of beam steering, beam focusing is something that we will cover in the next few slides. Okay.